So I was asked to present the work which is being carried out in our group at NIT Jalandhar. So I will start with the basic introduction, but I think we have heard excellent talks on this introduction part. So what is the motivation to study the internal structure of the hadrons? Then some basic light cone kinematics. So then after discussing the basic distribution functions, so I will discuss then the work which is being done in the meson sector as well as the baryon sector in our group. So it is very well known that to study this structure of hadrons in terms of these elementary quarks and gluons. So this is provided by quantum chromodynamics, and this knowledge of this internal structure will of course provide this basis for this understanding this strongly interacting matter. But however, this problem of confinement, it is still a very big challenge to perform these calculations from the first principles. So since at high energies the coupling constant is small, so QCD we can use it perturbatively. But at low energies, because of confinement, coupling constant is large. So we have to use other effective models to describe the physics in this energy region. And this of course has wide range of applications to study the dynamics of and structure of hadrons and nuclei. And new experimental tools are of course being developed continuously to probe this region, this non-perturbative region, and these hard diffractive reactions, semi-inclusive reactions, and other DVCS processes. So, but still this fundamental questions still have not been resolved, and it is still we are still looking into this most challenging problem in QCD. So these fundamental questions, what are the static observables, how are they related to each other, then what is there apart from the valence quarks, so how are the C quarks and their spins distributed inside the hadrons or nucleons specifically, then this role of orbital angular momentum of these quarks and gluons, and how they interact in the nuclear medium. So the driving question to study this hadron structure, or specifically the nucleon structure, was started from this proton spin crisis, where earlier it was assumed that proton having a 3 quark structure, so UUD. So this experiment in 1988, it gave that the valence quarks carried only 30% of the proton spin. So however, this other model calculations contradicted this result. So this was known as the proton spin crisis, and most of the physics after this proton spin crisis came up, so they have been trying to study this polarized structure functions in the deep inelastic scattering experiments and all. So all these experiments after this EMC experiment, so they have provided the evidence that the valence quarks do not carry the entire spin, and so it is confirmed that there is a quark C around the valence, there is a quark C inside the nucleons. So space-time of course is not an invariant object, and they are independently, space-time is an invariant object, however independently they are not. So then I will quickly go through this comparison of this instant form and front form. So in instant form, this all measurements are made at a fixed time, however in the front form they are made at a fixed light cone time. And the energy momentum dispersion relation is also different. So there is under root factor here and there is no under root factor here. And the vacuum of course is complex in this case and simple in the case of front form. So then we are using light front because there is no square root factor in this dispersion relation, and these are the terms which give you energy, longitudinal momentum and transverse momentum. And so this is basically an ideal framework to describe the hadronic structure. So I will just skip this. So this is just how we define the 4 vector in the light cone is light front time, light front space variable, and this transverse variable. And also we get this longitudinal momentum and energy. So this is a Hamiltonian method, and This is similar to the perturbative and lattice QCD, and we can connect it to the QCD Lagrangian directly. So coming to the next section, distribution functions. So we have this mathematical tool to unfold this internal structure. So we have parton distribution functions. So I will quickly go through this because we have discussed all these things. So we have this PDFs are the basic ingredients to understand the structure, and from these parton densities we can extract the distribution of the longitudinal momentum carried by the quarks, and they give information about the probability of finding this parton inside the hadron with this momentum fraction x. So they can be probed through this deep inelastic scattering processes, and we can write this correlation to evaluate the PDFs. But then how these partons are distributed in the plane transfers to the direction where this hadron is moving. So it is important to study this, through the GPDs. So these are the observables which can give you the 3D structure. So I think everybody has gone through these basic distribution functions. So they depend basically on 3 variables. This is the momentum transfer, longitudinal momentum transfer, and all. So in this case also we can write this correlation to evaluate the GPD, and in this forward limit of 0 momentum transfer, they reduce to the ordinary parton distributions. So they can be explained through various exclusive processes such as DVCS and hard exclusive meson production. Then coming to the transverse momentum dependent parton distributions. So we get the information of the structure in the momentum space. So they describe this probability to find this parton with the longitudinal momentum fraction x and transverse momentum with respect to the direction of the parent hadron momentum. And they are particularly important because they give rise to the single spin asymmetries. And this is the correlation to evaluate the TMDs of hadron, and they can be measured in this SIDAS and Rayleigh production. So this is this image from this Signori where we can see that it is like a fish bowl. This partons behave like fishes inside the fish bowl. So then we have Wigner distributions. So they give the joint position and momentum distributions. Then of course GTMDs. So this is a natural extension for the TMDs, and they depend on these 4 parameters. Sorry. Oh, this is going back or okay. So these are all the distribution functions and their interconnections. So we have computed most of these distribution functions except for this this fraction FFs. So for this case of baryons as well as the spin 0 mesons. So then coming to the research group at NIT Jalandhar. So there are, these are the students who have worked or they are working with me, and so now we are exploring this internal structure of mesons and baryons. So I've divided this work into 2 sections. Meson sector, so we have been working on pion, kaons and the d mesons, and in the baryon sector also proton and other members of the low lying octet baryons. So in this case we have done the calculations at the leading order as well as sub-leading order. So in the meson sector, so we have computed this Wigner distribution GPDs, TMDs at the leading twist, and they have been, the leading twist TMDs have been done in different front models. So this holographic model, then ADS QCD model, light cone quark model, and also we have extended this work to compute the twist 4 TMDs for the pions and kaons. And this is the, very recent work which I am presenting. So GPDs in the baryon sector have been computed at the leading twist, and the twist 3 and twist 4 TMDs, and twist 4 of course GPDs and GTMDs for proton have been calculated, and here also we have used different models. So work done in the meson sector. So this is of course clear why we are attempting to study the pions and kaons, because the new experiment, EIC experiment, will give this opportunity to increase this knowledge on the pions and kaon structures. So this is the model light cone quark model. So using this, and this is the other model used for this calculation of the mesons. So we have computed the U quark distributions for the case of pions, and this is for the case of twist 2 and twist 3 and twist 4 TMD. So this is corresponding to the twist 2 TMD and EQ for twist 3, and this F3 is for twist 4. And this is for the case of kaon. So again these at twist 2, twist 3 and twist 4. So the leading twist TMDs, they are spread over the wide range of longitudinal momentum fraction, and this higher twist TMDs, they have higher peak values as compared to the leading twist TMDs, and also they have they carry low longitudinal momentum fraction as compared to the leading TMDs. And for the dissimilarities, we have this for the leading twist, the average longitudinal momentum is larger as compared to this higher twist TMDs for the pions as well as kaons. So then this is the other model, light front holographic model. So here also this is for the case of pion, and there is a double peak here. So I will tell you those. This is for the case of kaons. And if we see the difference, so in this case, this double peak structure is due to the combination of these two states, and both the models, they give positive distributions. However, in this NGL model, there are few negative distributions as well. So this is the wave function. This is the TMD from the light cone quark model I have presented earlier, and this is for the light front holographic model. Now coming to the unpolarized TMDs, for the case, these are the plots for at fixed values of k-perp with respect to x, and this is for the case of pion. And for the case of pion, we have at a fixed values of x, so with respect to k-perp square. So these are the distributions. Then this is for the case of kaon for fixed values of k-perp, and then we have, this is for the fixed values of x-perp, x. So then comparison of the PDFs. So for the two models, so this is light front holographic model and light cone quark model. So this is for the case of pion. Then for the case of kaon, so these are all the PDFs. So we have also evolved the PDFs with the experimental data and this. So and I think today only we were able to get a better fit for this value at 0.22, I guess. So, but I could not update it here. So that even gives a better fit. So this is for the case of pion. So this is the comparison of the form factor with the experimental data, and for the case of pion, and for the case of kaon, there is not much experimental data available, but this is the fit here, and this is the comparison of the form factor ratios of kaon and pion. So we have also extended this work for the case of heavy meson. So D plus, we have just started this work, and my MSc student is also working on it. So DS plus, so this is comparison with the form factor result. So then the next is the work done in the baryon sector. So we have this TMD correlator for defined here, and these of course states are already known to everyone. This P and initial and final states of the proton, they having momentum with helicities lambda, Ni and Nf. And here in this light front quark diquark model, so proton is described as an aggregate of an active quark, and the other two quarks are taken as the diquark spectator, and we can express it in terms of this diquark singlet state, diquark isoscalar vector diquark state, and this last vector diquark state. So here the scalar and vector are of course S and A. So in this case also, this convention, the light cone convention is used, and the momentum of the proton struck quark and the diquark, they are given here. So these are the explicit wave functions, basically the states, and these light front wave functions corresponding to this plus half and minus half states. So these are listed here for the case of scalar as well as vector states. So these are the basic definitions. So we have adopted this wave function from the soft wall ADS QCD predictions, and these parameters have already been discussed. They are established as this equation. So these are the TMD parameterization for twist for proton at twist 3 for this chiral even and chiral odd part. So these yes. So then this explicit expressions for the TMDs are given here. So for the case of proton, this twist 3 TMDs are given in these equations, where these colored parts are for the S wave, P wave and D wave, and these are the other three. So this has been published last year. So then equations of motion corresponding to these TMDs have also been computed. So this TMD from the Gaussian ansatz average transverse momentum, and this are, they can be defined as follows, and these are the values corresponding to these parameters. Now for the case of U quark, this TMDs which have this Gaussian transverse dependence, so they have of course demonstrated the Gaussian factorization, and there is no direct connection between these waves being SPD and this with the applicability of this Gaussian ansatz, and also there is no direct connection between the equation of motion being quadratic in this transverse momentum. And so these are the TMDs. So by comparison, we have compared this explicit wave functions and this Gaussian, using this Gaussian ansatz. So these are the plots for that. So then coming to this TMD PDFs, so with respect to X, so these are the plots for this, and so this is for the up quark and the down quark, and the other four. So then this is the comparison with the light front quark model and this quark diquark model. So these are at different scales, and we can always evolute this for different scales. So the PDFs and TMDs. So this is the comparison with the phenomenology, and this is the flavor combination. This on this way where this only mass term contribution is there. So this is plotted with respect to this light front quark diquark model, which is evoluted to 1 GV square, and also this light front chiral quark model. So this is also at the model scale 1 GV square. So we have this class data which provides a good access to this scalar PDF. So we have compared this with our results, and we can also, we can definitely of course improve these results by considering the contribution from this quark gluon interaction term, which we are trying to do. So this is the publication. So then coming to the last section, so we have computed this for the baryon sector. We have computed it for the case of the spin half baryons. So where we have these strange baryons as well, the lowest lying spin half baryons. So here we consider this quark scalar diquark model, and these are the different wave functions, and yeah. So these are the results for all the members of these low lying octet baryons. So this is for the where the active quark is a U quark, and this capacity to carry this longitudinal momentum fraction varies with respect to, depending on how much strange quarks are there in the baryon, and here this is proportional to the object. It is proportional to its mass. So moving from p to lambda sigma plus sigma 0, so diquark becomes heavier and tends to carry more longitudinal momentum. So this is the case for the unpolarized GPD, where the active quark is considered to be a S quark, and this is again for all the members of the low lying octet baryons. And in this case also the amplitude is more for when the quark active quark is an S quark, and it carries smaller longitudinal momentum. An active S quark carries smaller longitudinal momentum fraction. Then this is the transversely polarized quark in unpolarized baryon, so where the active quark is a U quark. So in this case also the GPD is proportional to the baryon mass. More the mass of the baryon, the higher the amplitude, except for the case of this cascade particle where it is not the case. So then this is the transverse polarized quark in unpolarized baryon, where the active quark is an S quark, and in this case also the amplitude is more for the active U quark, and this active S quark carries smaller longitudinal momentum fraction. So then charge distributions can be computed. So in coordinate space and in impact parameter space, so we can compute them using the GPDs. And these charge distribution corresponding to different members of the octet baryons are presented here. And these other three. This is the case when this active quark is a U quark, and this is the case where active quark is an S quark. So the difference in the coordinate and impact parameter space, it arises because of the presence of this term in the expression, and the difference between this active quark being an U or S quark is smaller the amplitude of the active S quark, smaller is the contribution, and also the distributions, they fall very rapidly and it is localized in a very smaller region. So then this intrinsic magnetization moment distributions can also be computed where for the active quark being a U quark or an S quark. And in this case also the amplitude is dependent on it is inversely proportional to the baryon mass. So then this last part is the transverse distortion and single spin asymmetries. So this is for the transversely polarized baryon. Okay. So this we can always relate this non-zero spin flip GPD to this transverse distortion, and in accordance to this relation. So after I will just present the results. So this we have this dependence of this single spin asymmetries on this ELECTRON momentum fraction, and these are the plots. It's 10 minutes or? Yes. Okay. I have 2 more minutes, right? Okay. No, I think it's already. So for this U quark, this single spin asymmetry is recognizable at the smaller values of this momentum fraction delta, and so this is also we have computed these for all the members of the octet baryons, the spin half octet baryons. And this for the S quark, so we have this sigma baryon which has the maximum amplitude, and then there is cascade baryon. So the peak is shifted to this delta 2.52, and this is also due to the comparatively heavier diquark mass of this because this is USS and this sigma is a UUS. So this has a 1s quark, this has 2s quarks. So this is due to this heavier diquark in this case, and in the case of lambda, this is the amplitude is smallest again because of its mass. So this is the dependence of the single spin asymmetries of this active quark momentum in this case. So in this case also for an active U quark, so single spin asymmetries in sigma has a minimal difference as compared to this cascade, and there is a significant difference from the value of lambda. And for the S quark, again, this distinction between all the three baryons, I mean, there is a small distinction between all the three baryons, and they are again dependent on the masses of the baryons. So this transverse azimuthal symmetry can be compared with the experimental measured Hermes asymmetry, and we can, by introducing this kinematical factor, and these are the results for that for all the baryons. And the outcome of this is that the strange baryons and the trend of peaking position of this single spin asymmetries is the same as in the case of transverse single spin asymmetries. So yeah. So again, this is, we can also compare it with this by introducing this kinematical factor, and these are the results for that. So that's, thank you.
Questions? My question is that if you want to calculate twist 3 TMDs, you need gluon, right?
Yeah, I mentioned it that we have computed it without this gluon part.
So basically you don't have H tilde, E tilde that?
Yes, yes, it is not there.
We are calculating now that in the terms.
I mentioned it that we are trying to compute it now. Yeah.
But in your model, I think there is no gluon, right? How do you calculate these things then?
There is a modern development by Barbara Pasquini. We are using that model.
Oh, that's great. Very good.
Not in this model, but.
So yeah, I was particularly interested in the proton part, and you went a bit fast on that maybe. So I wanted to clarify, what is the difference between the Gaussian ansatz and the full calculation? Could you please?
This one?
Yeah. So is it coming from? So what is the coming from the model, and what is an extra ansatz?
This comparison, yes.
Yeah, exactly. So explicit means the one from the model.
Yes.
Right.
Yeah. And this is the solid line with this Gaussian ansatz. So they are more or less comparable. I mean, not very different.
Yeah, they are. Yeah, sometimes they are very different
yes.
though for some of the functions. So I wanted to understand what was this Gaussian ansatz. Okay, so so you mean that's multiplying? So I still cannot follow very well. So it's you're multiplying at the x-dependent part by a Gaussian, and the x-dependent part is coming from the model.
See with this, when we compute this average transverse momentum, so there is this, we multiply it with this term, this Gaussian ansatz.
Scalar PDF, you compare with the experimental data, right?
For the case of pions?
For the case of proton, I think E of X. This one.
Yeah, this is with the class data.
But the models, what is your model scale then? The data is available, I think 1.5 GeV. But your model is like 0.9 GeV square you are talking about.
So this is, we have evolved it to 1 GeV square.
But this, which evolutions you use in that case? Which evolutions came? I mean, is DigiLab or?
Yeah, DigiLab.
But this evolution is not work for this PDF, right?
Are taken from the initial scan from 0.8. That was taken by Tanmay sir's paper.
My question is that the ePDF is not evolved by DigiLab. It's a different evolution.
Thank you.